So, wow, things are moving pretty fast. We are in week 10. We're doing Lab 10 first order circuits as simulations. So you're going to really get drilled in first order circuits and their ramifications. Next week, we're going to actually talk about the final project, optional final project you can do. And we'll have a kind of a fun lab in applying what we've learned in circuits in a microcontroller situation, which is pretty interesting, and it's optional. And then lab practical is coming up in week 12. It might be nice to move that to week 11. Maybe I'll do that. But it depends on how much time I have, which is not too much. But I'm also behind in grading, so I need to focus on getting caught up in grading in this class, which I'll probably do this weekend. So according to my notes, this is a very hard lab. But it shouldn't be. It's all just simulation, but you're doing simulation and you are doing analysis, and you're using the simulation to back up your analysis. Some thoughts for next, well, the challenge is, you know, with first order circuits, a lot of times what we're asked to find is just the capacitor voltage as a function of time, or the inductor current as a function of time. But in this lab, you're also asked to find other values like, you know, some voltage across a resistor or current through some other resistor. And so these are variables that depend on VC and IL. So you have to treat, at that case, once you solve for VC, you still have to solve for VC or IL if it's an RL or a C circuit. You still have to find those first. But then you treat those as sources, like voltage sources that are just time varying. And then you apply the rest of your DC circuit analysis to those. I'm supposed to emphasize the need for debugging to find agreement. I think a lot of people would just like turn in their analysis that had nothing to do with the simulation, and they just like, oh, that's my answer. And you know, if there's a disagreement, you should track down why. And instead of suggesting debugging, I'm supposed to ask you to write down, even just the, you know, look at the initial value and the final value that you're getting from MATLAB, from your analysis, and circuit lab, and if they don't agree, then you have a problem that you should track down and sort out. So really, we're trying to get confirmation of theory with simulation in this case, but we're trying to get sort of an understanding that we can then, you know, find more confidence in our analysis techniques. Several people had the switch wired wrong in example 2, so it closed instead of opened. Be careful when you're wiring switches to make sure that they work right. And you know, one thing that's kind of interesting is that even though it's true that the inductor current cannot jump when you throw a switch, anything else in an RL circuit can jump. So other currents going through other resistors or voltages will jump at, they could jump at t equals 0. So be aware of that as well. Kind of interesting to that. Anyway, so we are doing Lab 10, and that is here. There were so many questions last year. I have this great index of the questions and the answers in video form. So there is, if you scroll down here, there is a video, this is for the online students. And there's in-lab Q&A, and then I took that Q&A and I made an index to all of the questions that I was getting in the different exercises. How do I find the effective resistance seen by the capacitor using a circuit simulator? You don't. You're going to compare the analysis of the transient curves that you derive, the solution curves, and make sure they agree. And you know, how do I actually do this lab? Well, there's a video question, someone asked that, and I show them step by step how to do the lab. I'm going to show you in here because I'm here, but this is mainly for the online people. I hope the online people will find this valuable. And A lot of questions come up on this lab. It's just, there's, I think it's complicated because we're doing these time functions, and if the time scale you're using is not quite right, then your curve's going to look off and stuff. So I'm assuming everyone here is going to do the Circuit Lab version. If you're interested, there is a PSpice version, and I don't mind which one you use. You will download the data sheet. Make sure you download it. Don't try to do it in the browser. And the link to all of the videos is in the data sheet as well. So we're going to go through the process of, pull up the lab. You're going to be doing a time domain simulation using Circuit Lab, and you'll be plotting a first order circuit response in Circuit Lab and MATLAB. So this is good. I mean, you can use this for real circuit problems. It's a really nifty, Circuit Lab I really like. It's just a great tool. I use it a lot myself when I'm doing some circuit stuff. So what we're doing when we're doing these first order responses, it's considered a transient response because it dies out after a certain period. It's not a steady state. It's something, we're changing from one state to another, and it's ephemeral. It doesn't last very long. And there is a demo circuit available in the lab, which has a switch setup in it already, a 10-volt source, a switch, a resistor, and a capacitor. A very simple circuit. And you want to click on that link to bring it up in Circuit Lab. And you'll want to log in using one of the login IDs available on the site. So in case you've forgotten, they are listed right here. Make sure you log in, because if you don't, you're only going to have like 5 minutes before it knocks you out. So I'm going to sign in myself with my own, not this one, I have my own. I think that's the login. Let's see. Shoot, now I don't know what my login is. Oh, maybe it's just the CAPTCHA. Let me see. You got to click the CAPTCHA. They're saying that you're not a robot, and then log in now. Okay, and then open it in the editor. And we're going to, let me go back here. Where's this lab handout? Oh, we're going to start by looking at this new element, which is a switch. So you can double click this switch and it will tell you its some of its parameters. Its name is SW1. The time that it switches here is at 0 seconds. You can see that. And then it also has a resistance you can model for its, you know, the resistance of the switch when it's on. And it's a pretty straightforward. So basically, what it's saying is at t equals 0, it's going to move from this position to this position, right? It's going to connect the voltage source to the RC circuit. Now it's the same switch. If you want a switch that opens at t equals 0, look at these 3 terminals. How would you wire the switch so that it opens at t equals 0? Sorry? No, what you would do if you want to make the switch open at t equals 0 is you could connect the wire this way. You see what I mean? If you look at it now, it's closed between these 2 terminals, but when it switches, it's going to open. It's going to go to this terminal, right? So it's the same switch, just how you wire it determines how it's going to behave. In PSpice, there's a different switch for one that's closed and then opens and one that's open and then closes. But in Circuit Lab, it's just the same. Questions on that? Okay. What else? Click on the Simulate button and open the time domain simulation pane. All right. So let's see. I'm going to zoom out a little bit on this guy and click on the simulation pane, and we want to click on the, oh yeah, it automatically is open to the time domain. There's different types of simulation. You can do a DC simulation like we've done before, a DC sweep, and what we're doing today is a time domain simulation. A time domain simulation is going to help us determine the transient response for the first order circuit. In order to run the simulation properly, you have to add values for the start time, the stop time, and the time step, the number of increments between the data points in the curve. It's actually going to be calculating the voltage or current at different times based on the numbers that you punch in for these values. So for this one, we're going to enter 0 for the start time, 0.01 for the stop time, and 0.0001 for the time step. There's a relationship that we want to follow here, right? The time step should be about 1/100th of the stop time, so that we get about 100 data points in our curve. On order, you want about 100 data points to make a nice curve. If you have fewer data points, it's going to be kind of jagged. You're going to miss some of the details. If you have a lot more data points, it's going to slow down the simulation. So we're going to say you want to start at 0, stop at 0.01, and have a time step of 0.0001. So start at 0, stop time is going to be 0.01, and the time step is going to be 0.0001. And then you have to indicate what circuit variables you want to plot. You can move the mouse to the top of the capacitor so it turns into a pen, and click on the black circle. That will give you V of capacitor 1 node A and I, the current going into it. That is sufficient. And I think I've already got these here. And when you have everything configured right, you run the time domain simulation, and you'll get a set of plots that are going to look something like these. And this is our transient analysis, and you can see that the voltage across the capacitor is going from 0 volts up to 10 volts. At the same time, the current is going from 0, and the current is actually jumping, right? You see the jump in the current, right? You see how the current is actually stepping? How come the current can step? Isn't there a no step rule? No jump rule? What happened to the no jump rule? Why is that jumping? Is that an error in the simulation? Mason?
No.
No, why not? Why can't it jump?
Because it's not changing the energy.
It's not jumping in energy. Yeah, current can jump, but voltage cannot. Is that what you're saying? Yeah, the voltage here cannot jump, but the current can. And I think based on my notes, I think we can start at a negative time just to kind of see that transition. That's actually kind of cool. Let's hide this. You can hide the figure and go back to your simulation. And suppose we started it at negative 0.001. Okay, we'll start with a little bit of a negative time, a little before the switch has thrown, and let's run this again. And oh, we didn't get any negative data points. Let's start a little bit further back. Negative 0.01. It's not showing. Huh. Thought we could see negative values. Well, we could actually maybe move the switch time forward just to kind of experiment here. Suppose we actually change the switch time to switch, instead of it switching at 0, have it switch at like 0.001. And now you can kind of see it, right? You can see the capacitor voltage didn't actually jump, but the current actually did jump. And that's true, that can actually happen. The current can jump, but the capacitor voltage cannot jump because that would take an infinite amount of energy to do that. You can see there's a bit of a, it looks more like a ramp here, but what we're seeing here is the space in between two data points. This is one data point, and this is the other. If you want this to be more accurate, you would actually reduce your step size in your simulation, giving you more points in the curve, right? Right now, the step size is that we're getting 100 data points. Well, that may not be enough to get a good view. You could reduce the step size another factor of 10 and run the simulation again. And now it looks like a serious jump there, right? It's jumping straight up. The current is changing instantly when the switch throws. Okay, but the voltage cannot jump for the capacitor. For an inductor, it's going to be the opposite. The voltage could jump across the inductor, but the current cannot jump. The inductor current cannot jump. Once you get that, you know, it's kind of good, I think, maybe to keep the switch changing at 0, because it's going to be kind of confusing otherwise. One thing that could, whoops, I don't want to look at switches. One thing that, oh, interesting. One issue that people run into when they're doing these problems is they might do a situation where they, for some reason, they set the stop time to like 0.001. And if you run the simulation now, you're going to find that your curves look like straight lines. Okay, so if you see a curve that's a straight line, what does that mean? What does that mean if you see a curve that's a straight line? Transient curve that's a straight line. Mason, you were going to say something. Yeah, you didn't extend the time window far enough to see the full transient response. If you get a flat line, it means your estimate of the time constant is way off. And in general, what you want to do is you want to go out about maybe 5 time constants in your simulation. You know, it takes several time constants for an exponential curve to decay to close to its final value. So you're gonna, and you're doing your analysis, you're gonna estimate what tau is. And if you multiply that by 5, you can use that pretty much as the end time, the stop time of your simulation. Because after 5 time constants, you should be close to your final value. Does that make sense? So 5 times tau is a good idea. What's the time constant of this circuit? 1 microfarad is C and 1 kilo ohm is R, right? When you close that switch, this, you know, the Thevenin resistance seen by the capacitor is going to be 1K, right? So the time constant tau is going to be what? R times C.
1 millisecond.
Yeah, it's going to be 1 millisecond, right? R times C is going to be 1 millisecond. So our stop time, we put at 0.01. That's actually like 10 time constants, right? And when you run it, this is what 10 time constants looks like. That's actually good. That's reasonable. If you did 5 time constants, that would be a half of this, right? 0.005. And you know, that's still showing you the full transient. 5 time constants is good, 10 time constants is good for your stop time. But you're going to link up, you got to link it up to that time constant. Otherwise, you're going to have a really strange. You also might, if you go too far, like suppose you take your stop time out to, you know, 0.1 seconds, you're going to see something that looks like that, right? The transients died down really fast, and it's kind of hard to see when that actually took place, you know. So you want to get a nice curve that shows like maybe 5 to 10 taus in the sample. Okay. This kind of shows you, yeah, if you're too coarse, you're going to have these kind of jagged steps, so you want to refine it more. You can also, and this is where a lot of people kind of got confused. You can compute and plot mathematical expressions involving circuit variables. For example, if we want to plot I of t over 4 for some reason, you can add an expression and enter I of C1 dot node A divided by 4 in the box. So this would be here. You can add an expression, and you can say I of C1 dot NA divided by 4. This will allow you to calculate other circuit variables in the circuit. If there was something that, you know, or you want to do a voltage divided by 4, that would be a current, maybe maybe that would be more reasonable, like a V of C1 dot NA divided by 4. If that was some current in their circuit, you can use that to find the current. Maybe the current through the 1K resistor. You know, you can do divided by 1,000. Well, that should be the same as the current going through the capacitor. But anyway, that's the idea. You can also find, you can click with your device here with your pen. Like if you want to find the current going through R1, you can just do I of R1 dot NB. That's the current flowing into node B of the resistor. And it's helpful to hover over the resistor terminal because it usually tells you somewhere in there what you're looking at. I don't see it.
Not the build first.
Oh, is that what you got to do? In build mode, yeah, when you hover there, that's R1.NB, right? You can see that on the lower right. And so if you put your pen there, you're going to get the current flowing into the resistor through that node. So that'll give you the directionality of the current. If you want to see the current going to the left, you would click on this node with your pen. That would give you the current flowing into node A of the resistor, which would be flowing to the left through the resistor. So the polarities are important. And then when you do the simulation, you'll see those plotted on the same curve. And I need to change my simulation parameters again. So you'll see multiple curves there, and it'll label them with a legend on what they are. Okay, you're also going to do the same thing in MATLAB or using FreeMat, and you want to make plots. This is telling you, okay, if your analysis says this is your equation for the response of the voltage, and this is the current, and you want to plot these, you would start out by making a vector of time. Notice the way the time vector is defined. It's the same way the simulation is set up. We have a start time, which is 0, a colon, and then this is the step time. This is the increment between points in your vector you're creating, right? And then a stop time, which is when you want that thing to end. And you're going to get a bunch of data points in T when you do that. If you bring up FreeMat, you can try that out real fast. If you type that time command without a semicolon, you'll see all of the data points you get, and you can see that the space in between them is 0.01. If you put a semicolon after it, then it will just do it for you and not print out the results. So if you type in this expression for V and I using exp to raise e to the power, as a function, it raises e to the power of something, and you plot it and all that stuff, you're going to get a plot that looks like this. And so what you're going to do is you're going to try to you're going to derive the formula for these things and compare it with your simulation and plot it in MATLAB and put both plots in there and make sure they agree. And yeah, that's the plan. So let's look at so there's problem 1. There's only 3 exercises. 1, 2, and actually there's just 2. There's just 1 and 2. And this is where you have to be aware of this. So this one is actually asking us, problem 1 is asking us to calculate I/O of T. That's the current through the 4K resistor. But be aware, you're asked to find I/O of T, but you got to focus on, when you have an RC circuit, you got to solve for the capacitor voltage first. And then once you know what that is, you can then determine what I/O of T is from the capacitor voltage. And in your analysis in all these things, you're going to find the initial voltage across the capacitor, the final voltage across the capacitor, the equivalent resistance seen by the capacitor when the switch is closed, find the time constant, construct the equation, calculate I0 from VC, and then plot it, and then do the same thing with simulation and show your schematic, show your simulation results, and then look for disagreements. You want those to be the same. All right, that's the rundown of the lab. Any questions? Questions? So what I would recommend is start with the analysis and then do the simulation after you've kind of got a sense of what the analysis says. So spend some time using your circuit analysis techniques, find the initial value of the voltage, final value of the voltage, do all these steps, construct it in MATLAB, and then do the circuit simulation. If you have two lab partners, you might have one person do the simulation, the other person do the analysis, and then come together and see if you can get them to agree. So this is the circuit that you are simulating for number 2. It's kind of confusing for people to get. There we go. But you can simulate it. I'm not sure how to, there's a way to plot stuff, and I wish all this other garbage would go away. Let me see if I expand that. There we go. And then there's that's just doing a picture. There's a way to plot stuff. It's been a while since I used this thing, but anyway, when you run it, this is it starting out. You know, you can do mesh analysis. It'll show you the current going down the 12 ohm and down through the inductor is the same. It's 3/4 of an amp. This is called every circuit. And those come together and go through the switch and go up through the 12. You got 1.5 here, you got 3/4 here. But then, sorry? I think they are indicating, I don't know, they're indicating maybe the direction of the flow. I don't know what they are. But then what happens is you click on the switch, and this is sort of what's happening. So, you know, you can see when the switch opens, what's going to not change? The inductor current. Everything else can change instantly, right? And when you do that, so here I'm going to click the switch, boom. All of a sudden, the current flipped in the 12 ohm resistor to go 100% in the opposite direction because the inductor was still driving it, right? And no current anymore in this outer branch. It's been disconnected. But eventually, and I'm not sure the time scale here, eventually the 6-volt source is going to take over and start driving current the other way if we wait long enough. And if I could plot it, I would show that. But you can see the current's kind of going slower and slower. And eventually it will turn around. But yeah, I don't know what those purple things are. What are these things? Going slower and slower. Oh, there's a time clock here. What does that do? Simulation speed. Oh, I could speed this up too. So if I speed it up faster, you can see it's going faster and faster, 2 milliseconds per second. That's the time speed. See, eventually, it's going slower and slower and faster. Let's go to make this thing go faster. So eventually, now the 6-volt source is kicking in and making it go the other way. So when the transient settles down, the current is going back up through the 2 Henry, but it's less. It's like 0.37 instead of 0.375. So that's what's happening. And let me, I'll anchor this thing at 10 milliseconds per second and redo it. So we can back up and start all over again. Oops, I gotta close the switch. I guess I have to undo. No, No, I got to redo all the, okay, there. I don't know how to close the switch any other way, but anyway, getting back to here, and then starting this, and then changing the simulation speed to 10 milliseconds per second. And there it's going, 10 milliseconds per second. Now I flip the switch and boom, you know, it's still initially going in the direction of the inductor, but then you can see it's getting slower and slower, and then I don't know why it's jerking like that. And then it's flipping going the other way, right? Because the voltage source is taking over, ultimately making the inductor store energy again, but going in the opposite direction. Yeah, isn't that cool? That's very helpful to be able to see that. And as you're working with circuits, you can start mentally visualizing that. You know, this is what I do when I start working with circuits. You can start seeing these things moving through it. So anyway, continue.